All right, today we're going to do problems 6 through 10 on worksheet 4. If you need problems further on, just go to the next worksheet. All right. Gaseous sulfur dioxide can be removed from smokestacks by treating with limestone and oxygen. So we're supposed to name the compounds in this reaction. Well, clearly that's sulfur dioxide because we just talked about that right here. And this is limestone. But the proper name for limestone is calcium carbonate. You should know that, calcium carbonate. Calcium carbonate. Now, this clearly is oxygen, or sometimes known as oxygen gas. And this one is calcium sulfate. And this last one, of course, is carbon dioxide. So, you should be able to name all of those. All right, so it asks what mass of calcium carbonate is required. Well, that's right here. Calcium carbonate is required to remove 150 grams of sulfur dioxide. So we're looking at those two that are right next to each other. So we have 150 grams. Notice it has a decimal point after it, which means there's 3 sig figs. That's important because we're going to want 3 sig figs in our answer. We have 150 grams of sulfur dioxide. We have to get rid of grams of sulfur dioxide and go to moles of sulfur dioxide. This is just a standard stoichiometry problem. We have to go from moles of sulfur dioxide to moles of calcium carbonate. Remember, we can't just switch grams to grams. We actually have to go through moles because we have to use our molar ratios that we talked about in our previous podcast. And then we have to go from moles of calcium carbonate to grams of calcium carbonate. All right, so what do we know? Well, we know we have to go look up sulfur dioxide and figure out how much it weighs. Okay, and sulfur dioxide weighs 64.064 grams in 1 mole. Now we look up here at our coefficients, and our coefficients are 2 and 2. So that's easy. And 1 mole of calcium carbonate, we have to figure out how much calcium carbonate weighs. And when we actually go out to our periodic table and figure all that out, that's 100.09 grams of calcium carbonate. So when I do the math, I come up with 100. Let's try that again. I do the math, I come up with 234 grams of calcium carbonate. All right. How about if I'm going to calcium sulfate? Well, calcium sulfate's over here. This side of the equation doesn't matter. The thing that does matter are the coefficients, and again, we're dealing with a 2 and a 2. So let's go ahead and start with 150 grams of sulfur dioxide. Now notice the left portion of this is going to look exactly the same because we're still converting from grams of sulfur dioxide to moles of sulfur dioxide. And then we still have to get rid of moles of sulfur dioxide. So all of that is exactly the same as what we saw previously. But this time what we want to do is instead of going to calcium carbonate, we want to go to calcium sulfate. So we want to go to moles of calcium sulfate. And that's again a 2 because we have a 2 up here in our problem. All right. And then finally what we want to do is we want to go from moles of calcium sulfate. We want to go to grams of calcium sulfate. So we're going to have to figure out how much 1 mole of calcium sulfate weighs. So if we do that and we look it up on the periodic table, that's 136.14 grams of calcium sulfate per mole. So if we do this, we end up with 319 grams of calcium sulfate. Okay, that's it for problem 6. We'll go on to problem 7. Okay. Let's look at methanol. Methanol is liquid, it's alcohol. It's one of those things you often find in the medicine chest. Methanol, ethanol, there are different types of alcohols. They're clean burning, and what we're supposed to be doing is it can be made by the direct reaction or the direct combination of carbon monoxide and hydrogen gas. So if I take carbon monoxide, which is a gas, and I add it to hydrogen gas, which clearly is a gas because it just told us it was a gas, right? What we are trying to produce is CH3OH. Right, so as we try and do this, we say, well, I have one carbon on both sides, and I've got one oxygen on both sides. I've got 4 hydrogens on the right and only 2 on the left. So I fix that by putting a 2 in front of the hydrogens. Right? Oh, by the way, we were told that methanol is a liquid. So, okay? All right, so now we want to do B. Starting with a mixture of 12 grams of hydrogen and 74.5 grams of carbon monoxide, what's the limiting reagent? Okay, well, let's start with one of them. Let's start with hydrogen. And we're going to start with 12.0 grams of hydrogen. Now, what we do when we start with that is we have to convert from grams of hydrogen gas, to moles of hydrogen gas. And then from moles of hydrogen gas, we have to go to moles of a product. Well, we only have one product, CH3OH. And because down here we can kind of look ahead and say we're looking for masses, we're looking for our theoretical yield of methanol, and we really kind of want to do that in grams, right? So that would make sense that we would still make one more change here and go from moles of methanol to grams of methanol. All right, so we need to do some math here. We need to figure out that 1 mole of H2, you can figure that out pretty easily. 1 mole of H2 is 2.0158 grams. And when I'm converting from H2 to methanol, I have a 2-to-1 relationship. And then I can figure out that 1 mole of methanol has a mass. Well, I add up the 12 plus the 4 plus the 16. And I do it with a little bit more precision than what I just gave you, but that would be 32.042 grams of methanol. So if we actually plug all this stuff into a calculator, we get 95.4. 95.4 grams of methanol. Well, now our problem is, this was H2, what about carbon monoxide? So we have to go through carbon monoxide also to see what happens. Right? And we're starting with, let's see, 74.5 grams. 74.5 grams of carbon monoxide. So we have to convert all of that to, again, we have to convert it to methanol. So let's go through the process. We go from grams of CO to moles of CO, and then moles of CO to moles of ethanol, and then from moles of ethanol to grams of ethanol. All right, so I have to figure out how much carbon monoxide weighs. And carbon monoxide weighs 28.01 grams per mole. And my mole of carbon dioxide to moles of methanol is 1-to-1. They cancel each other out. And we already know, if we look at the problem right above us, we can see that we have 32.042 grams per methanol in 1 mole. If I do the math here, I come up with 85.2 grams of methanol. So that tells me that this is my lower number down here, so I must have run out of carbon monoxide before I ran out of hydrogen. That's what that tells me. Right, so what's our theoretical yield? Our theoretical yield is right there. It's 85.2 grams of methanol. Now, what mass of the excess reactant do we have? Well, we didn't use all the H2. Because for H2 could have made more methanol, but it didn't make more methanol because we ran out of carbon monoxide. So we take the 95.4, because we want to figure out how much we have left over. We take the 95.4 grams, and we subtract the 85.2 grams, which we actually got, right? And we get a total of 10.2 grams of methanol. Everybody see that? We're looking at these numbers over here. We're subtracting them. We're coming up with 10.2 grams of methanol. But now what we have to do is we have to convert back over to hydrogen, because hydrogen is what we had in excess. So if we start with 10.2 grams of C3, CH3OH, methanol, we have to convert going the other way. So we have to go from grams of methanol, CH3OH, we have to go to moles of methanol. And then from moles of methanol, we can go to moles of our target, which in our case is H2. And then we go from moles of H2 to grams of H2. Alright, well, what are my numbers? Well, I know that 1 mole of methanol weighs 32.042 grams. And I know that I'm going from methanol, which has a 1 in front of it, to hydrogen, which has a 2 in front of it. It's up there, so I have a 1 to 2 relationship. And my grams of hydrogen per mole, we did that as well. That is 2.0158 grams of hydrogen. So if I plug all this in my trusty calculator, what I come up with is 1.2 grams of hydrogen. 1.28 grams of hydrogen. So this is what we did not use. That's the stuff we had left over. So when the reaction was all done, we still had 1.28 grams of hydrogen sitting there in the flask, or however we were going and combining this. Alright, this is a very interesting drawing, and it can be pretty confusing, but what it's trying to do is it's trying to mimic the reaction of nitrogen plus hydrogen giving you NH3, which is ammonia, which we've already talked about this reaction. But what this means is for every mole of water, or for every molecule mole of nitrogen or molecule of nitrogen, it's going to take 3 molecules of hydrogen to bond with it to make 2 NH3s. So for example, here I have 2 NH3s. I've got 2 nitrogens. Right there I've got 2 nitrogens, which is N2, and I need 3 H's, and so there are 3 H's. So 3 H2s. So those 3 H2s, which are white, are going to bond with the blue N2, and they're going to make a product, okay, known as ammonia, 2 NH3s. Right, well, I'm going to do the same thing over here. I'm going to have a nitrogen and 3 hydrogens. They'll bond together. And then I'll have another nitrogen and 3 hydrogens. They bond together. And then I have another nitrogen and 3 hydrogens, and they bond together. And notice that here, and the one up and to the left, that one right there, there are some nitrogens left over that didn't get used. So now what I'm looking for is a picture that looks kind of like this, but my nitrogen is going to be a blue dot with 3 yellow dots coming off of it. Right? NH3. Right, so I'm going to have 3 white dots coming off of that one. Alright, so let's see what I have. Here I've only got 2 white dots coming off, so that doesn't make sense. Here I've only got 2 white dots. Here I've got white dots floating all over the place. That doesn't make sense. Here I've got some ammonia, but when I look at the ammonia, I've got more than I would think I should have. I should only have, 8 ammonias sitting here. Right? And then I have to have 2 of these guys left over. So let's look for some place where I have 2 of those left over. Well, I've got 2 left over right here. There's one that didn't bond, and there's one that didn't bond. So that looks pretty good. That might be it. Over in number 6, I've only got 1 of those, and in 5, I've only got 3 of those, which means it's got to be this one. Now, what actually happened? If I look at that nitrogen split up, and so I've got a blue nitrogen and 3 white ones, but then I still have another blue one and 3 white ones. So these 4 nitrogen molecules should give me 8, should give me twice as many ammonias. And down here I can see that I've got 1, 2, 3, 4, 5, 6, 7, 8. So that makes a lot of sense. So our answer here is number 4, which is the correct representation of what we're looking for. Alright, so what did I run out of? Well, I definitely did not run out of nitrogen. I ran out of hydrogen. I ran out of the little white ones. They're gone. Alright, they're all bonded. So hydrogen is my limiting reactant because that's what I ran out of. not nitrogen, not ammonia, and they are not in the correct ratios. All right, let's try number 9. Styrene, it's a hydrocarbon. If it's burned in oxygen, okay. Excuse me, CH plus O2 gives me CO2 plus water, H2O. Right? I'm trying to figure out the empirical formula for styrene. Interesting. So how do I do that? Well, what I have to do is, if this is going back into a previous unit, but I have to start, let's see, this is styrene, oxygen produces 1.481 grams of carbon dioxide and a bunch of water. All right, so what I have to do is I'm going to start with my carbon dioxide, that's 1.481 grams, and I want to convert that into carbon. Does that make sense? So let's look at what we have. We have 1.481 grams of carbon dioxide. But how many moles is that of carbon dioxide? Well, I can convert from grams of carbon dioxide to moles of carbon dioxide. I still don't see it. I still don't see where it matters. Oh, well, if we then go and we say, well, I want to get rid of moles of carbon dioxide, and I want to go to moles of, in this case, I want to just go to moles of carbon. Because there is a one-to-one relationship between this carbon in this atom and how many moles there are. Right? So there's 1 mole of carbon in a molecule of CO2, or a mole of CO2. Right? And how much does a mole of CO2 weigh? Well, I have to figure that out, and that's 44.009 grams. When I do this, I come up with 0.0337. And what is that? That's moles. All right, well, let's do exactly the same thing with 0.303 grams of water. All right, so I now take moles, grams of water, to moles of water. I go from moles of water to moles of hydrogen. Now remember, we're dealing with water, and water has a molar mass of 18.015 grams in 1 mole. And 1 mole of water gives us how many hydrogens? Well, think about it. H2O has 2 hydrogens for every molecule of water, so I'm going to have a 2 up here because I'm getting 2 moles of hydrogen out of that 1 mole of H2O. When I go and I do this math, I get 0.0336 moles. All right, folks, as far as I'm concerned, that's about as close as you can get to a one-to-one relationship. Okay, so we're going to look at C and H because we figured out how much C we have right here. There's that much C, and there's that much H, and since those numbers are virtually identical, our empirical formula is going to be 1-to-1, which means we have something that has an empirical formula of CH. Okay. This one is a rather tough one. So let's go through this. Boron forms an extensive series of compounds. They're in B, X, H, Y. We're going to use the same concept we just used to go back and do this one as well. Okay. So we have an unbalanced reaction. And we have, over here, we have 0.148 grams. And we have 0.442 grams of this. And over here, we have, don't know. All right. So I think we're good. So now what we have to do is figure out what our relationship is between boron and hydrogen. Okay. So the easiest thing for us to do as a start is to go and calculate how much boron there is in our reaction. Well, how in the world do we know that? Well, we know that we have, over here on the right, we know that we have 0.442 grams of boron dioxide, whatever, right? So what we have to do is we have to figure out how many grams of boron that is, because we know that's 422 grams, of boron trioxide or boron oxide, whatever you were going to call this thing. I don't even know what it's called. I guess diboron trioxide, maybe. But anyway, we can figure out how much boron that is. All right, so let's try that. 0.422 grams of boron trioxide and I have to get rid of grams of boron trioxide and go to moles of boron trioxide. All right, well, that part's pretty straightforward. We can figure out how much boron trioxide weighs, and it happens to weigh 69.619 grams. Right? But now what? We have moles of barium oxide, but we want moles of barium. So what we do is we say that 1 mole of barium oxide, boron oxide, is going to give you, well, look right here, and we notice that we have 2 moles of boron in every mole of boron trioxide, or whatever it's called. So that would mean that we have that would mean we have 2 moles of B for every mole of diboron trioxide, or whatever it's called. Okay. Now, we want to figure out how many grams we have on the left. Right? So, for example, this tells us how many moles we have. But now if I take 1 mole of boron and go to grams of boron, right? Grams of boron is 10.811 grams of boron in 1 mole. Right? And why do we care? Well, again, this is one of these really hard thinking problems that we say, well, how in the world do we go and approach it? The boron that's all over on the right-hand side had to come from somewhere. And it came from over here. And this is the only compound that has boron in it. So based upon that, whatever boron's on the right, exactly that same amount has to be on the left. So in our case, this tells us that we have 0.131 grams of boron on the left. So what's the rest of it? Well, it's got to be hydrogen. So 0.148 minus 0.131 gives us 0.017 grams of hydrogen, because that's what's left over. All right. So we know how much boron there is and how much hydrogen there is in terms of grams in this substance. So let's go and work backwards now. Let's go and take one more step to find our empirical formula. Well, we know that 0.131 grams is boron. And if we convert grams of boron to moles of boron, right, that tells us how many moles we have. We know that 1 mole of boron is going to be, we just figured that out a minute ago, boron is 10.811. And we also have, we also have the hydrogen, which is a very small number. It's 0.017 grams of hydrogen. And again, what I have to do is go from grams of hydrogen to moles of hydrogen. Grams of hydrogen, moles of hydrogen. And because it's H2, I'm sorry, this is not H2. Those are just H's. My bad. 1 mole of hydrogen weighs 1.0079 grams. Okay. So that gives us a number. Well, let's plug them in the calculator, see what we get. We get 0.0121, and we get 0.0169. Well, I'll tell you, buddy, I can't go and figure that out. Those numbers are outside my pay grade. So how in the world do we do this? Yes, we take the smaller one, which is the 0.0121, and we divide both of them by 0.0121. We divide this by 0.0121. Right? And when we do that, the top one, of course, is equal to 1. But the bottom one is equal to 1.4. 1.4. Well, if it's 1.4, what is that? That's 4/10, that's 2/5. That means I have to multiply these numbers by 5. So if I take them both and I multiply by 5, I get 5 on the top, and I get 7 on the bottom. 5 on the top and 7 on the bottom. Okay, so I get B5, H7. Now, folks, we'll never give you something that complicated on a test because that would just take too long, unless it was one big word problem, which is possible. But just want to let you know that was a long, hard problem, and hopefully you did pretty well on it. Okay. Anyhow, that's it for this particular podcast. See us in class if you have questions. And the next podcast we start question 11. Have a good one. Bye bye.